Okay, so the previous video was MRTS, and this will be the second and I think final video for MRTS. So this is like a marginal rate of technical substitution continued. But we did fine. It's just if we just kind of quick say it, this is kind of the accumulation of the last video, just that one mathematical statement. There's two of them. And we kind of explained it a little bit better right now. The one on the left is much more common, I think, than the one on the right. But they're both the same because you can flip the understanding. But let's kind of do a quick example and we'll just review this and actually probably define it a little bit better than we did in the previous video. So specifically, the previous video ended page 39 here. Yeah, this graph here is where we ended the previous video. So we kind of note very simple things here. I don't know if we can say more common, but this is going to be capital as a function of labor, and this is labor as a function of capital. It literally doesn't matter how you do the convention. I mean, as far as a three-dimensional graph is concerned, they're literally the same. As I said before, I think the one on the left is more common, and how they kind of define it down there, that's using the one of the left. But we shouldn't let the notation trip us up. It's just the same problem twice, and you can do like a LK or you can do a KL. But these things are precise. In other words, if we have on the y-axis, the vertical axis, if we have capital as a function of labor, then it will always say LK. Whereas if we have labor as a function of capital, it'll be MRTS, and they'll just flip it, K comma L. So this whole little K comma L does specifically go to him, mark my words. And this L comma K does specifically go to capital as a function of labor, but it's just notation, and you know, we're supposed to get it right. If we make a mistake and flip the convention, it's not like it matters or something, but what do all the symbols mean? It does nothing for our grade or anything like that, and we're supposed to know, but it's also who cares. Okay, so we do want to remember though, yeah, we can kind of derive this really quick. Yes, I'm looking at this thing on the left. We can kind of read an example that used just little integers, but it's stupid. But remember this, I'm looking at MRTS, yeah, LK. Okay, so if it equals him, you know, right there, if it equals that right there, then that's going to be the partial Q. We did this last time. I just didn't write it out, but I'm just reviewing the thing from before. But the marginal product of labor is the partial of Q with respect to L, and then the partial of Q with respect to K. Yeah. So what happens if we have the KL? Yeah, if this is L comma K, what happens if we have the other graph? It's just going to be the opposite. Let's just kind of do one, yeah. So if we flip it, it is going to be, just go ahead and flip this fraction here. I think I can do a better job than that, can I? MRTS with, we can go back in the video, it uses that graph on the left. Therefore, it's going to be L comma K is going to equal the partial of what? The partial of Q with respect to L divided by the partial of Q with respect to K is going to equal negative. It does have to be rise over run. So if it's the graph on the left where K is the up, it has to be negative the change in K over the change in L. So this is negative. The rise over run is negative because the slope from the graph of Cobb-Douglas is always negative. Therefore, negative the graph. You know, these are the silly little things that I hate it when I get stuck on some random screen here. Yeah, apologies. Yeah, but so if it's negative, then negative the thing, of course, is a positive number. Therefore, this is always positive and this is always positive. It's okay to call MRTS the absolute value of the thing, but it's also meaningless because really it's the negative of a negative slope. Therefore, those are always going to be positive. Okay, so that's all we need. You only need one, but the other one literally just flips the understanding, right? The other one is marginal rate of technical substitution. They come up with this fancy name. What it means, who cares? will of course be, that should be the partial with k. So that'll be the partial of q with respect to k over the partial of q with respect to L is going to equal negative delta L over delta K. If we want to pause and see the beauty, that's all fine. But that's it for marginal technical substitution there. Marginal rate of technical substitution. So the outcome to all that stuff I just wrote is written here. The one on the left is for the left graph, comma. The one on the right is for the right graph, and it doesn't matter which one we use. So they do have this thing, yeah. Let's see if we can kind of skip ahead. I want this to be the final video here for this. But I'm not sure if I'm skipping anything important. We can kind of read that if we want, yeah. So they do have this concept for all three that we did in chapter 2. All three of these are in the book, but the Cobb-Douglas, the one on the left, law of diminishing marginal returns, that one is the most important. Yeah. But what is it? It's just the graph. It's just negative, the whole MRTS, whatever it is. It doesn't matter if we say it right. We're not saying kind of. To get the changes, and we have to remember derive the derivatives. But the slope is negative, so it is just the negative of the slope. That's all it is, yeah. So all it is going to be the negative of the slope on this graph. So what is it going to be over here? Yeah, for the linear isoquants, we call them perfect substitutes is what this one is going to be. Well, it's a straight line that only has one slope. So it's going to be negative the slope. Remember, this one has a different slope at any given point, which is what most of homework problems would be Cobb-Douglas on the left. But the definition doesn't change if the graph changes. It's still the slope, and it's the same slope everywhere because that's a straight line. Yeah, this doesn't seem like a slope. We don't care about this, believe me, and we don't care about this. When we have this thing, you know, where we're making a bronze or something like that, or brass, or you need two different metals to make an alloy, and it only works in exact, you know, this is the example where you're making kind of an alloy, and it only works if you have exact proportions. If you have too much of one, it's just going to sit there, and you have, you know, more of one, but the same amount of the other being used. We only care about that. It doesn't appear as though there's a slope there, but there is. Yeah, because what do? You just have the total k. It doesn't count. It's still going to be a derivative divided by a derivative, but you still have the changing k. We don't care about this example as much. I just choose not to define it that well. Whether it's technically a negative or not, I don't know, because we just have one point right there, and I don't care. But it's still like the height in k, you know, the length in L. Or maybe we just call it k over L. Whether or not there's a negative is who cares. But that one point, the k value there, the k value at that point divided by the L at that point, and we do have there, you know, different isoquants. They only draw one, but there are like different isoquants where we have this little line going and all that. We define this one the least because it doesn't matter in the book. But the definition is the same for all three graphs. That's what I say. Where we do care about the left, the Cobb-Douglas, the most. Yeah, if we just kind of carefully scroll through, they're just going to describe those graphs there. Yeah, so we have the DRMS, diminishing rate of technical substitution, which is just the same as the law. I'll mess it up if I say it, but the law of diminishing marginal returns, it's just the exact same thing from the Cobb-Douglas. They describe the perfect substitutes, perfect complements, which is the other two graphs. We do just want to kind of fly through this a little bit and get to what. So they do all three graphs on one graph. That's kind of a little conclusion. But next video is going to be the cost function, and that's where we want to get to now. I will see you in the next video.